Welcome back. So yesterday in the last lecture we were talking about that how drainage pattern can help us in inferring or delineating the subsurface structure or lithology. Now this is the area, as I told before, that close to Chandigarh, and we have the Indo-Gangetic plain this side, and then you are having a very sharp boundary which marks the plate boundary between the Indian and the Eurasian plate, and we have Shivalik hills which we say upper Shivaliks or sub Himalayas. Now in this region particularly, when we were doing survey, so before going to the field we prepared a basic preliminary geomorphic map, and in this preliminary geomorphic map what we found was that the drainages in some area were showing a typical radial pattern. We were a bit surprised to see this, that why in a flat area we are able to see such radial drainage where there is no dome, because in particularly if this area which you are looking at here is the region over here. So this is an intermountain valley between the two hill ranges, which is known as Son Dune. As I have already told that these dunes are the local terminology used for valleys, intermountain valley. So we have Dehradun, Pinjore Dune, Son Dune, similarly like that, and even the Kathmandu is a valley. So within this valley, how it is possible to see that there is an radial drainage? At the same time, what we also looked at, because we were mapping some tectonic features, and these are the traces which we have marked as the active fault traces, and this you will learn in the next part of this course, that part 2, where we will teach you how to identify such landforms and all that and tectonic features. But in here I would like to very briefly mention that this fault lines or the tectonic features we marked, and we got very impressive signatures of this ongoing deformation on the surface, okay, and that is very well preserved in the drainage. So let us see the close-up view of this area, what exactly it shows us actually. So this is again a panchromatic image of Pinjore Dune and Son Dune, and the river which is flowing here is your Son river. Okay. So this is you having the Sirsa river which is flowing, and it is a tributary of the major river Shatluj. Now you can, if when I'm putting my cursor here, you will be able to trace out some boundary over here. This is what we have marked as an active fault, which goes like this here. I'll show the close up of this, but before going to this part, let us look at this region. Okay. Now if you look at this region here, this portion, a very good example which shows a typical radial pattern. So what we see, if I trace out these streams here, then you will be able to mark, like, let me take another color. So if I trace out this drainage is here, you can see this goes here, smaller one is here. I'm just quickly drawing the major ones so that you can now. What pattern you see here is that this is an elevated portion in the center, and then you have a radial drainage which is flowing in all directions away from the center. So, this was one of the indication which we took into consideration, that this is a typical upwarp area. So, we decided to go in field and check that whether this is okay or not. Okay. So, this location is known as Dhana, and then this is the area known as Nalagad, and the fault trace which we finally conclude that it passes through this here and then further here. So, these arrows are marking the trace of the tectonic feature. Close up of this, if you look at, then what you see here. Okay. So, I will just remove this drainages so that it is clear. So, this is the trace here which we marked. Okay. Now, what you are able to see here is that on the right hand side of this line, that is what we call the fault line, you have a very tight meander. So, if you see the meanders here, it is very tight, but as soon as you crosses this line, then you are having very almost straight channels. So, this is a clear example that the block on the right hand side is the hanging wall, and it is getting deformed as compared to the foot wall on this side. So, this is your foot wall and this is your hanging wall, and then fault trace goes somewhere over here. So, you can easily demarcate such features on the earth surface using the drainage pattern also. So, channel morphology plays a very important role in identifying several such features. So, let us look at this one, that is close to Dhana, the field example of this. Okay. So, this is what we have already discussed. Now, go to field, and then this is what we saw. So, it is clear cut warped area which was showing as the radial drainage pattern. Now, we discussed few drainage patterns, and here there are listed more. So, I request you to go through it, but few we will see we have already discussed. And as I told that some of the drainages will indicate you the lithology, either the area is comprised by homogeneous material, or it is in flat lying, or it is fractured with an right angle. Okay. Either the drainages are flowing in the folded terrain where you have weak and harder rocks. So, and some of the examples are of parallel drainages which are very much similar to the consequent drainage which are developing over the slope. So, these are few more subgroups or subtypes and the main types which has been given here: dendritic pattern, subdendritic, pinnate, rectangular, angular, parallel, trellis, radial, centripetal, angular, and the description of the same has been given here. So, I would request you people to go through it and we can move ahead in this course. So, for example, the rectangular drainage, if you take, okay, and most commonly found is a dendritic, but you look at a rectangular stream having right angled bands. So, what does the geological significance is? Joints and fracture, example in sandstone and quartzite. Sandstone is sedimentary rock, quartzite is a metamorphic rock. Okay. Then if you look at the dendritic pattern, irregular branches of stream haphazard resembles a tree, okay, tree like pattern. So, it is in homogeneous material, horizontal beds, gentle slope, etc. So, go through it. This will help you in interpreting your observations which you will be doing based on the satellite photo interpretations. Now, drainage basin evolution and morphometry drainage patterns, we will see few examples here which will help us in inferring our observations. So, fluvial geomorphology, we have linear aspects of the channel system, then aerial aspect of the channel system or the drainage basin, channel geometry, and then process domain. Okay. But we are not going to talk all here, but few which are important for us we will discuss. So, the linear aspect of channel system, if you take, usually what we look at is the basin area, is on the surface area, drainage pattern we are interested in, and the stream order. Now, stream order, of course, you can use because most of the hydrologists will use this in quantifying the stream network, and which is useful for the flood hazards and all that. Okay. And even though this can help in identifying the subsurface lithology. Then coming to the bifurcation ratio is also important, how the lower order and higher order streams are been seen in the basin, how they are distributed. Then drainage density will again play an important role in runoff. When there is a heavy rain, then this will play an important role. Okay, the drainage density. So, if you have to look at like any drainage basin, as we have been talking about, that each major trunk stream will have its own drainage basin, and of course those smaller drainage basins which we can call them as a sub basin. Okay. And this is the boundary, what we call the basin boundary of this trunk stream, and within that we have smaller tributaries. So, smaller streams joining making the next higher order stream, this is what has been shown here, this is what we call stream ordering. So, we have at the place where the basin or the river originate or the smaller tributaries originate and goes and meet the major one. So, you have the first order stream, you have first order stream. So, when two first order stream meets at a point, the downstream portion of the river will become the second order, and similarly if two second order stream meets, then it becomes third order, two third order stream meets, then it becomes fourth order, and this is how the ordering has been done. Okay. And you can then calculate the, based on the stream order, the number of streams you are having. Say like first order you are having 16, and this will help you in getting the bifurcation ratio, okay, of the basin area. So, area on land that contributes surface water to a stream, like this is a drainage basin identified based on the topographic divide, okay, also called as the watershed or the catchment area. Okay. The watershed boundaries are called drainage divides. This is the example for that. So, you are having one stream here, another one here, this is the major stream, and of course, they are the tributary of this major one. So, this are the sub basin of this stream actually. So, this is the divide between this basin and this basin here. Okay. So, this is how it has been shown that you have major streams and then you have the sub basins of that, and this is shows the drainage divide between the two drainage basin. So, you have one basin here, another one here. So, you are having the streams flowing in this direction, coming here and meeting the major streams, okay, similarly like that. So, those are the smaller tributaries of that main trunk stream. Now, as I was talking about that, how about the headward erosion and the development of the or you can say the how the basin will evolve, okay, over the time. Now, this is a very simple example which has been given here. Of course, you need a slope and you need a precipitation. Okay. So, once formed, that channel erode, okay, and lengthen its area, okay, or it will keep on adding the the more streams here. That is, the channel network forms by bifurcation of headward eroding channels. So, what has been shown here, that over the time same amount of precipitation there is, slope is the same in 2 hours, in 4 hours, 8 hours. What is happening is smaller streams are developing slowly and slowly, and what you are able to see is that this is the fixed point, but the drainage is evolving in the headward side, okay, so towards the upland. So, this is what you can look at, the development of the drainage basin. Now, this is an example from Great Run of Kutch, which shows a very typical example, smaller basins, and all, if you see a very typical tree like features here, okay, typical tree like features you can see over here. So, this is what we call this as a dendritic drainage. You have the main stream, and then you are having the tributaries. So, slowly what will happen will that this keep of this will keep on growing actually. So, next it will grow here, this probably will merge, and then so on, okay. If you look at the close up here, so you have smaller stream. Now, another important point is that since we classify that looking to the pattern, we say that this is an dendritic pattern. So, this indicates that there has to be an homogeneous flat area or homogeneous material within flat surface. Of course, yes, this area is comprised of mostly the tidal flat material or the tidal flat deposits, which are almost homogeneous, silty clay, mostly in fine sand. So, there is a homogeneous material which also is reflected in the dendritic pattern. Now, this observation just to show that how over the time the river or the fluvial system will evolve and different landforms will be formed. Okay. This we were doing field in Andaman, and what we observed was that when the sea water was coming in, this is a beach here, and then flowing back. So, while going back, there is definitely what we see in a slope break in the slopes here. So, if it will return back to the ocean, of course, what you will be able to see is that distributed network, and this is what we were able to see, and this is typical of delta what you see in the major system or the major rivers when they are meeting the ocean. Okay. So, what we found is that we have the channel here. I will show the close ups where I will show the terraces and all that. So, this is on the very miniature scale, very small scale, but we were able to see some fascinating landforms here. And then you are having braided system over here, you are having braid bars, you also have meandering system here. Okay. Let us see the close up somewhere over here, what we are able to see. Yeah, this one. See, this is then what I was talking about, the river bank. So, you have a terrace here, and then similar terrace continues here, but over here you have a meander and you have multiple terraces. So, one is this one, another is in this one, and third one is sitting here actually. So, these how the terraces will form over the time. Okay. Now, quantifying stream network. Okay. Stream order, usually what we say is that streams in a basin can be ranked using one of the several schemes. Okay. So, we have, this is one of the scheme which I have already discussed. So, if you are having lower order streams, then you have joining the two lower order stream joining, giving rise to higher order streams. Okay. Now, if we have to come up with a bifurcation ratio, as I told, that we can have number of streams, and then you can, based on the number of streams of a particular order, you can talk about the bifurcation ratio. Now, what is the bifurcation ratio? Let us look at this. Okay. So, it has been denoted by RB, which is equal to NU by NU plus 1. So, NU is the number of segments of a given order. So, if you are having given order 1, then you will have that number, and then nu plus 1 is your number of segments, that is the stream order of the next higher or the highest order. Okay. So, you are looking at the ratio between that. Okay. So, which forms the basis of, this is on the basis of Hutton's law of stream numbering. So, if suppose you are having nu is 10, then nu plus 1 is 2 here. So, for example, what you are taking is this one second order stream and this one is the first order stream. So, you are having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, 10 is your first order and then you are having second order. So, next higher order is your second order. So, you are having 3 streams of that. So, the ratio between the first order and the next higher order will be your 3.3 and so. Okay. This is useful in some cases. Okay. So, this is how you will be able to see the first order and the second order ratio, second order and the third order ratio and so on. Okay. Now, this is important when people are talking about the discharges and all that, like the flood intensity. So, flood intensity is considered to be a discharge along a channel over the time, and flood intensity will be influenced by the rate of runoff. Okay. So, if the runoff is very high, then also you will have floods, but if runoff is very less, then you may not come across the flooding event. Okay. So, the channel pattern and the shape will also play a role along with the runoff. The number of tributaries, that is what we were talking about, the bifurcation ratio, as well as this will also talk about the drainage density and the distance. So, when you are extracting the information of any drainage basin, this can be kept in mind. Okay. This can help you in talking about the whether this area will have higher floods, and the intensity of the flood will be higher or less, that you can talk. Okay. So, in stream order, the smallest tributaries are designated at first order, this we have already discussed, and those where first order tributaries joins, okay, to first order, then you have second order and the third order, so on. Okay. So, usually it has been observed that low order streams have shorter lag time between rainfall and flood. So, when the rainfall start, when the precipitation, the water falls on the surface, okay, then the time taken by the lower order stream will be very less, because they are very short, hence the time lag will be very less. So, they will have the bank full flow very quickly as the rainfall started and the between the flood. Okay. And are more prone to flooding. So, you will have, if you are having large number of higher order, lower order stream, then also it is not good actually, whereas the higher order streams with many tributaries are less prone to floodings. Okay. So, this is an in general it has been understood that this will happen. Okay. Now, drainage morphometry and discharge, if you look at this is one of the example which has been given here, that usually it is what has been seen, that if you are having the higher bifurcation ratio will lead to the higher is the discharge, and the lower bifurcation ratio lower is the discharge. Okay. But as I told that the discharge will depends on the shape of the basin, the distance, that is also again very important, and the runoff in the region, that is the lithology will also play an important role. Okay. So, drainage network of river basin shape and channel pattern are the most vital morphometrical factors that play significant role in increasing the rate of flow through the drainage system. Okay. So, with this understanding, let us see one example was what exactly happens. Okay. However, even with higher bifurcation ratio, okay, or higher bifurcation values, in elongated basin, the hydrograph is very smooth, suggesting less discharge. So, hydrograph is again the time lag, and then you are having the amount of precipitation you are having. Okay. And similarly, in terms of the rounded basin with the same basin area with low RB value shows higher discharge. But what we were talking here, that if you are having low RB values, then you will have low discharge, but here low RB value shows higher discharge. The reason is here, for example, so one, you are having the elongated basin where you have the RB value is quite high, that is the bifurcation ratio is quite high, and this is your hydrograph. Okay. So, if you look at this one here, so what we see is the bifurcation ratio for this elongated basin is almost like 10. Okay. So, what we should have expected is a higher RB, higher discharge at this point. Now, what has happened is that if you see the hydrograph here, it shows very smooth. So, the time lag is quite high between the flood, peak flood and the rainfall and over the time. Okay. So, this is because of the distance. So the smoother area, or the rounded basin is having very fast peak. We get that like the flooding event at even with the lesser RB values. Okay. So what are the reasons for this? So one most important reason is the smoother curve of the narrow shaped basin. This is, we are talking about this one, with higher bifurcation ratio, that is 10, okay, can be explained by greater time lag. So the time lag was much higher for the water to reach the outlet. This is an outlet here. Okay. Whereas the time taken from the upper, middle and lower reaches in the rounded basin, because the basin is rounded, so the distance are shorter. Okay. No doubt the area is almost same, but that plays an important role. So upper, middle and lower reaches, the rounded basin is less, so the time is taken by this region is less because the resistance is less, okay, causing higher discharges. So this also one can keep in mind. Now aerial morphometric relationships, if you take, this is a very extremely important one, is the drainage density. Okay. Now the drainage density is been considered as it is based on the drainage basin area 1, and then drainage density D is the ratio between the total length of the streams. Okay. So all streams you take into consideration, you sum up which are you encounter within the basin and the drainage basin area. Okay. So what you are doing is that you are having, there is a basin area here, and then you have the major stream, you are having smaller streams here, so what you are doing is that you are taking into consideration the ratio between the total length. So you will take the total length of the streams which are available irrespective of their order. So you will consider that, you sum up this and then you will take the ratio between with the drainage basin. Okay. So it has been given as the D, the length of the channel per unit area, it is given in kilometer per kilometer square. Okay. So you are taking length per kilometer square area. Okay. So it has been given as sum of all length of the streams which you will encounter within the basin by the basin area. So this exercise also we will do it, and you will try to identify that what is the drainage density of that particular basin. Okay. So we will do one lab on this. Now this is along with the drainage density, this is another important part which we call as a drainage texture. Okay. So the drainage texture is defined as relative spacing of drainage lines. Okay. Commonly termed as coarse, medium and fine. So in terms of the coarse, what you have is the low drainage density develops on hard resistant rocks or over highly permeable material. Okay. Then you are having medium, moderate density develops on hard rock with moderate permeability. Fine, closely spaced develops on loose or poorly cemented rocks, example like material like clay, also silty sediments with a low permeability. Okay. So, what does that indicate? That low permeability and high permeability here, that it will allow, so when there is an rainfall or water comes on the surface, it will percolate down into the ground. Okay. So, if it is percolating down very fast, hence we are having a highly permeable material, so it will give lesser number of streams developed over the surface, that is will lead to the low drainage density. So, you will have low drainage density and you will see very few streams on the surface, hence you designate that as an coarser drainage texture. Okay. Medium, you are having, for example, in granite or sandstone, but in terms of the shale is the material with the rock with the low permeability. Okay. So, what is happening is that the stream will keep on, the water will keep on flowing and carving the surface and will result into the closely spaced drainage developed. Okay. So, this will give you some like similarity of dendritic pattern, but it will be closely spaced. So, I was showing one example from Great Run of Kutch that shows very typical drainage, which is we can texture, which we can classify as an fine texture of, or the drainage, fine drainage texture. So, this also can help you in identifying. So, in terms of the metamorphic rocks, this is gabbro, you will have mostly the coarser drainage texture. In granite you will have medium, and sandstone also medium to fine, but in shale you will have fine drainage texture. Okay. So, in short, the drainage density, the measurement of the drainage density provides an hydrologist or a geomorphologist with a useful numerical measure of landscape dissection and runoff potential. So, if you are having highly dissected landform, so you can also talk about that this area is having more number of streams, okay, and you have the potential of runoff may increase. Okay. So, this can also helps in identifying that what is the subsurface geology. So, on a highly permeable landscape with small potential for runoff, okay, because if it is permeable, the runoff will be too less. Okay. The drainage density are sometimes less than 1 kilometer per 1 kilometer square. So, this is in the case of the permeable. So, everything whatever the water is coming in, most of the water is getting percolated. Then on highly dissected surface, drainage density of over 500 kilometer per kilometer are often reported. So, these are the areas where you are having high drainage densities. Okay. So, closer investigation of the processes responsible for drainage density variation have discovered that number of factors collectively influence the drainage density, where these factors includes climate, because if you do not have enough water you will not have drainage development, topography, if you do not have slope you will not see any drainage development, soil infiltration capacity, if you are having porous material or porous soil then you will have very quick percolation and you will not allow the formation of the drainage. Of course, the vegetation can play an important role and the geology what we are talking about here, but here we can say that okay fine, let us talk about the rocks and the soil also. Okay. So, if you are having harder rocks you will not be able to see much of the drainages are forming there, like what we were looking in gabbro, metamorphic rock we are having very coarse drainage texture. Okay. If infiltration dominates over runoff, tends to have lower drainage density. Okay. So, if you have very high infiltration rate, then you have lower drainage density and you will have coarser drainage texture also. Okay. So, this is one example. If you look at within the same basin, at some location you have very low drainage density, and this was the reason because this portion of the area is comprised of sandy hills. Okay. So, sandy hills again, it is a porous material, loose material. So, the water coming on the surface will faster get percolated down and you will not see much of the drainage development. So, this shows that this area is having coarser drainage as well as the drainage density is very less. Okay. So, sand promotes infiltrations, results in the low drainage density. So, I will end here. Thank you so much.